Hi, and thanks for joining. My name is Peter Rickhaus. I'm working as an application scientist at Qnami. Qnami is a startup that is based in Switzerland and was founded as a spin-off from the Malatinsky lab at the University of Basel. The talk will be about exploring nanoscale magnetism using a scanning NV microscope. If we talk about nanoscale magnetism, there's a variety of compounds or magnetic orders that come into mind, and what distinguishes them is the surface magnetic field that they generate. So for example, antiferromagnets, they generate tiny fields at their surface, which are on the range of maybe 10 microtesla, whereas thin film ferromagnets may generate actually quite significant fields at their surface. Resolving the small surface field is a challenge, and these pictures that you see down here give an impression on this challenge. I'd like to focus on this antiferromagnetic spin waves that you see on the left side. It's a BFO SSO compound, and what you can see is a spin ordering, which forms these beautiful waves with a wavelength of 200 nanometer. So what you need to resolve these features is the ability to measure tiny surface magnetic fields with a very high spatial resolution. Now I would like to discuss a few examples of devices where this ability can be exploited. It can be, for example, in antiferromagnetic spintronics, where you may have the need to resolve really tiny fields at the surface, or what we have already seen, to resolve spin waves, you need a very good spatial resolution plus the ability to see the small tilting of the magnetization at the surface. Other examples are 2D magnets or MRAM, and I would like to give you now a few examples that have been published in literature using scanning NV microscopy. So the first one you have already seen, these are the spin waves in BFO. Another one are these fermions that you see as black dots here. And these fermions, they were found in an exchange biased stack. And the interesting thing is that they stabilize at room temperature. Yet another example is chromia that you see here. Chromia is an antiferromagnet, but you can controllably move domain walls in this structure. And the domain walls you can resolve using scanning NV. Here you see these black bars, they are patterned on purpose. And what the authors did was to move the domain wall either on the right or on the left side of this bar, and like this define bits that could be potentially used for computation applications. This is an example of a 2D magnet, chromium telluride, and you can see that the magnetization in this material is in plane. And this came as a surprise when people looked at this material and could be resolved using scanning NV. Yet another example is here this antiferromagnetic MRAM device, where the domain wall structure of the functional part was resolved. And could be used for further improving the device. So our solution to resolve these small magnetic fields is to use quantum sensors that are based on NV centers in diamond. And these NV centers or NV defects, they give the color to the diamond. So what is this color center? The NV center, if you look at the crystal structure of diamond, there's one carbon atom replaced by a nitrogen atom, and next to it is a vacancy. And this NV center can now capture an electron and then forms an interesting structure, level structure. What is peculiar about this is that the ground state appears bright in the fluorescence spectrum, whereas the excited spin polarized states are darker. And the transition between the ground state and the spin polarized states can be driven using a microwave. So what we record in scanning NV microscopy is the fluorescence as a function of this RF frequency. And you see that whenever you hit the resonance frequency with one of these levels, there's a dip in the fluorescence. And this allows to actually see the splitting between the two spin polarized levels. And since this is directly proportional, to the magnetic field that the NV center is exposed to, it gives you a very good sensor for small magnetic fields. What we now do is to put the NV center at the apex of such a pillar. So what you see here is the Qnami quantilever. This entire piece here at the bottom is carved out of diamond, and we shape this sharp pillar into this diamond bar and implant at the apex of the pillar one single NV center. Now the quantilever you can put into our microscope, the Qnami ProteusQ, to do the scanning of the surface you're interested in. So this is a full AFM with full AFM capabilities. The platform is provided or powered by Horiba, and we have an accessible, easy-to-use software and the microwave Q, which provides the full quantum control of the NV center that you need. So to summarize, the Qnami ProteusQ is really the instrument to measure tiny magnetic fields down to a few tenths of microtesla with spatial resolutions that go down to 20 nanometer. And the technique is entirely non-invasive, as opposed to, for example, magnetic force microscopy, where the tip itself is magnetic. Here we have diamond, which is of course non-magnetic, and it doesn't disturb your sample or the magnetic structures at your samples. It's a turnkey solution that is easy to use, has full AFM capabilities, and can be customized and upgraded according to your wishes. So if you're interested in learning more about the ProteusQ, feel free to scan the QR code to access the brochure or the spec sheet, visit our website, or drop us an email. We would be extremely interested to hear from you which materials you're interested in, which samples you're interested in, and we could get in contact and discuss whether this can be measured with scanning NV. So we'll be very curious to hear from you more about your devices. Thank you for listening.